We have now considered a brief introduction to Newton's laws, and so we're ready to start looking at solving problems. And when we do so, we idealize the models for our problem solving. We make them a little bit simpler, because if we included all the other concerns that we are instead simplifying, we could run into big trouble early on here. So we want to understand, just like with, say, projectile motion, what are the equations of motion not considering air friction, which really adds a great big complexity. So, for instance, we will neglect air resistance typically, also neglect the buoyant force of air, consider ropes and cables massless, although not all the time. We'll consider surfaces frictionless, although specifically sometimes we'll consider them with their friction, and that finite size objects are usually represented as points rather than considering their rotational characteristics. We'll consider that later. So I'm going to give you a little user's manual, quick guide, quick setup here before I show you how to do this by diving into some specific examples. Our problem solving strategy will start with a simple sketch focusing on the body that we're going to analyze. We're going to draw a free body diagram for it, including all the forces on the body, not forces by the body. Hopefully you understand what that means already. It's a big difference. Forces on the body. Then we're going to construct a rectangular coordinate axes. We'll resolve the forces into components. Often we'll snake out the original not to get ourselves confused, and double count force vectors. And do that for all the other objects that are of concern. Then we write sum of F as ma in both the x and y directions, because they're true in both of those dimensions separately, and solve for the unknowns. And ask ourselves, is this answer reasonable? If not, we may want to take a second look and see where things went wrong, and if the units are consistent. All that should hold true. As we now look at some examples, you can feel free to look ahead in your notes and try and determine which problems you really want to go through. Hopefully it's all of them. I'd prefer you went through all of them. You probably can use a brush up for each of these problem types that we're going to look at. Nevertheless, you have the option. So there'll be a whole slew of them before we're done here. So let's dive into the first one here, which is an elevator of mass m, moving upward, having an acceleration a. Cable mass is neglected. So two situations. In one, the elevator is going to be speeding up, and the other, it's going to be slowing down. And we're going to figure out the tension in the cable in those two situations. So here's our elevator, mass m. The acceleration is upward. Let's draw a free body diagram. So the two forces acting on it are the weight, mg, the tension acting upward, that we need to find out. Now, since it's speeding up, we know that acceleration is upward and the tension is greater than the weight, or it wouldn't be speeding up, would it? Since it's moving upward and speeding up. Well, the sum of the forces is ma, upward I show. So I'm going to show the acceleration next to this. So we start with the larger force, which of course is T. We start with that force. This tension minus the weight, T minus mg, is ma. Simple as that. Rearranging, T is equal to m times g plus a. So to interpret this physically, the tension equals two jobs that it has. It has to support the weight mg, then also provide the acceleration of the mass ma. So mg plus ma. Now when we're slowing down, the free body diagram looks similar. The weight is exactly the same, but the tension is less. In fact, less than the weight. Acceleration is down. This time, when we write sum of F as ma, we start with the largest force, which is mg, subtract off the tension, and that gives us ma, and here's our result. Simple as that. Okay, in a similar vein to the last problem, we're going to consider a parachuting clown. Ooh, that's kind of disturbing, isn't it? This parachuting clown doesn't have much of a parachute. Perhaps he's relying on his snorkel to provide some extra protection upon the impact of landing. I'm not sure. In any case, the parachute drag force reduces the acceleration. Its mass is 80 kilograms. The parachute provides a 340 Newton upward force. What's the acceleration? Let's apply the free body force diagram rules, which are adding all the forces. We got weight, we got the air force. Mass is 80 kilograms, acceleration down. The mg, the weight, is greater than the force of air friction. We're not told how fast he's going. Certainly a particular speed would be needed for this to take place. We're not concerned about that right now. Sum of F is ma. So we start with the larger force, mg. This force minus this force is ma. There you go. Same procedure. Solve for a. Mg minus F air over m, which is mg over m, which is g, minus F air over m. 9.8 minus 340 over 80. 5.55 meters per second squared. For our next problem, let's consider a factory worker pulling on crates with 500 newtons of force. And we're going to determine the acceleration of the crates and the tension in the rope. Connecting the crates. And our worker is very tired, pulling with 500 newtons. So there's the tension. First thing, free body force diagram for the man. So here's the man. Now I'm going to draw a bunch of forces on here. Let's just start drawing all the applicable forces. This is the force of man on rope. Hopefully you'll agree with that. This is the force of the rope on the man. Rope is pulling on the man that way. Gravity and the normal force. Now one of these forces does not belong here. Can you guess which one it is? It's a real force, but it's not one of the forces that should be on the free body force diagram for the man. And that is the force that does not act on the man, which is this one here. Force of man on rope. Yes, the man is pulling on the rope, but that's not what is happening to the man. The rope on the man is the real correct one. And then this one and this one are indeed both forces acting on the man. So, just want to make that clarification. Now let's do the FBFD for the crate. First crate, we have the weight and we have the normal force. Equal and opposite, plus the tension of the rope. The rope is pulling on the crate to the right. Crate number 2, we have the weight, we have the normal force, and the tension pulling to the left. So make sure you understand how this tension works. The tension consists of equal and opposite forces anywhere along this rope. At the point of contact of the box, the tension of the rope is to the right. On this one, the connection point on the box, it's to the left. So from the point of view of the boxes, that's the direction of the tension. All right, but we also got the force of this rope on this crate, so we added that one in as well. And now we're ready to figure out the particulars. So the acceleration of the crates, tension in the rope, connecting the crates. So here's what we have so far. And we recognize that the y forces all add up to 0, so we don't have to worry about those. So sum of Fx is ma. The acceleration of the whole system is the total amount of force divided by the total amount of mass, which is the 500 newtons of force that the man is pulling on this system of crates, right? Now don't worry about what he's doing to the earth with his feet, because that's really not considered part of the system right now. 500 over 100 is 5 meters per second squared. What's the tension? Let's determine it from the point of view of crate 1. Sum of F is tension. That is the sum of the forces on crate 1. These cancel out. So that's M1A. The tension then is 200 newtons. Let's confirm with crate 2. For crate 2, we've got slightly different situation. We have this force minus this force. The man's force on the crate, and actually it's the rope, and then the tension in the opposite direction. Subtract those two off, and you get m2 times a. Solving for the tension, 500 minus 60 times 5, 200 newtons. Voila, they match. Okay, how about a problem with a moose on a ramp that's angled 20 degrees from the ground? Let's check that out. Yes, that is a real moose sound. Okay. So the moose is hooked onto this cannon. The ramp is 20 degrees from the horizontal, and then the angle of the rope from the moose from that ramp is 30 degrees. So how large a force is necessary for the parallel part, the part along here, to be 800 newtons? And then how large is the F in the y direction? Well, this really is not much more difficult than any other ramp problem you've ever done. So let's take a look at it. So we have, from the cannon's point of view, we are going to define x, the coordinate system, along the ramp. And so, of course, x is 20 degrees from the horizontal. That'll make things quite easy. We already know that this force is 800 newtons. And so from this 30-degree angle, we have a force that provides or produces that 800 newtons. So what's that force? We know that Fx is 800, so Fx is 800, and that's just F cosine of 30, and therefore the F size of F is 920 newtons. So what's Fy? Well, since we've defined x already, y is perpendicular to that, and so it's just this component here. And so Fy is the force, which we know what that is now, sine of 30, and that gives us 460 newtons. Let's do a static equilibrium problem. And in this case, the sum of the forces equals 0. So that means particles at rest are moving with a constant velocity. In this case, we've got some cables attached to a rigid wall system, a nice engine hanging from these cables, 40-degree angle here. So we have tension 1, tension 2, and tension 3. Now, when you're going to choose a point that's in equilibrium to do a free body force diagram, well, you're usually doing it on an object, right? But avoid the following problems. So here's a point. You may ask, well, what are we really applying the forces to here? Well, what can be considered, since it's ambiguous right at the moment, consider a free body forces, but not action-reaction pairs. So, for instance, the weight is acting on the engine. Very good. That's a free body force. Moreover, T1 acting on the engine, that's also a free body for the engine, but it's not an action-reaction pair. Okay. Also, we have action-reaction pairs but are not free body forces. So, case in point would be the force of engine on the cable. So the engine here is applying a force to the cable, okay, pulling on the cable at this point here. And then, as a reaction to that, the cable at this point is tugging upward on the engine. So those are action-reaction, but not free body forces. We're usually concerned with the free body forces. Now, the object that we're going to consider in equilibrium, in fact, is the ring. The ring right in the center. So we don't have to have the free body considered to be forces acting on one of the physical objects. Right? So we're going to construct x and y axes and draw a new free body force diagram of all forces acting on, not necessarily the body of mass, but this particular point. So here's x, here's y, there is the ring. And we have T1 acting down, we have T2 acting to the left, and we have T3 at 40 degrees in this direction. So T1 is weight. And that's pretty self-evident from just observing this. The tension is equal to the weight of the engine. T2, what's that? And what's T3? Well, we have to do a little more work here. So let's resolve the force vectors into components, crossing out the original. So we have this T3 cosine of 40, and T3 sine of 40. We wiggle out the original, and we have everything resolved into perpendicular components. So the sum of the forces in the x direction is certainly 0. There's no accelerations going on. And in the x direction, we have t cosine of 40, that's this component, minus t2 will give us 0. And sum of the forces in the y is also 0. So t3 sine of 40 is this much, that much right there, minus t1, that's equal to 0 as well. So let's work with that and solve for t3, which is then t1 over sine of 40. And since t1 is the weight, it's weight over sine of 40, which is 1.56 w. There's our answer, 1.56 times the weight. Finally, t2 is t3 cosine of 40, and that's equal to t3 is t1 over sine of 40, so t1 over sine of 40, cosine of 40, and of course t1 is just w, so you can go w times cosine of 40 over sine of 40. In any case, you get 1.19 w. So those are the answers to the tensions in all the cables.